let me begin by introducing the subject. The subject is resonances. And we have seen actually a little bit of this in the resonant transmission of the Ramsauer-Townsend effect. Because of a resonance phenomenon within the square well obstacle, somehow for some particular frequencies, for some particular energies, the particles were able to zoom by without experiencing any reflection whatsoever. So let's begin the subject of resonances by asking a question. If you have the usual potential, the short range potential, which means that for some distance r greater than 0, the potential is 0. Here we put a barrier, and over there could be anything, some potential. We've computed this concept of time delay. There's a formula for the time delay. In fact, it was given by 2h bar d delta dE, the time delay. 2h bar d delta dE. And we discussed that this time delay can be positive or it can be negative. If it's positive, it really means a time delay. You send in a wave packet and it takes time to come back. More time than it would have taken if there had been no potential. You see, the time delay, you have a packet coming in from time minus infinity, and then it bounces back at time equal infinity, but nevertheless, you compare that with a situation in which there's no potential, and you see that there is some time delay. If you time the wave packet to reach at time equals 0 here, it will not reach back to where you were by time, by whatever time. Suppose you have the wave packet here at t equal minus 10, then it goes here and it delays, and at t equal 10, the packet has not reached. There is a time delay, a positive time delay. A negative time delay is the opposite. The packet arrives a little earlier. And the question I want to ask you, if you have a negative time delay, can it be arbitrarily large? Well, if you send in a wave packet, it may find an infinite wall here, and then it may bounce, and then, yes, it comes back earlier than you expected, because the free packet would have gone here and back. But you wouldn't expect it to be able to come earlier than if there was an infinite wall here, because there's no infinite wall here nor infinite wall here, so it's just not going to bounce before it reaches here. The best it can do is bounce when it reaches here. So you should not expect, and this is sometimes called causality, there's nothing that can make it bounce until you reach here, so you cannot expect that the time advance is larger as if it would have bounced before reaching the obstacle whatsoever. So this is important. We cannot have a negative time delay that is infinitely large. So in fact, the time delay, as we're writing here, should be greater than the total travel distance that you may save. If you bounce here, you would save at 2r over v, and you must be greater than that negative number, which is the total travel time that it would take to go back and forth here. So we can do a little arithmetic here. This is equal to 2h bar d delta dk, and here dE dk this is still greater than or equal than minus 2r over v. And I want to put a sim because our argument is not completely rigorous as to what's happening when it reaches here. It seems very plausible classically, but there's a little bit of a correction if you do it exactly. So it's not an exact inequality we're deriving. And what is the E decay is h bar times the velocity times the velocity. Remember, the E decay, you're differentiating h squared k squared over 2m, and you get hk, h bar times hk over m. So therefore, this is h bar and the velocity, and the h bars cancel, the velocities cancel between these two sides, the 2's cancel, and you get the d delta dk must be greater than or equal approximately to r. And that's sometimes called Wigner's condition on scattering. And it basically is the idea that the time delay, the time advance cannot be too large. Okay, so now we can ask the second question. How about the time delay, a true time delay? Can it be very large? Can it be arbitrarily large? Suppose you have a barrier of this form, and now you send a particle with a little bit higher energy here. Now this particle is going to have very little kinetic energy, so it's going to travel quite slowly here and go back. And this time it's going to delay quite a bit, probably. But the problem is if you increase, there's nothing very peculiar about this. If you go a little lower, then you're advanced, and then suddenly it gets delayed. It's not that elegant. But the phenomenon of resonance is precisely what we get when we sort of trap the particle, and the delay can be, as far as it seems, arbitrarily large if you design well properly. But the thing that we have to design, the example of what we're going to design, is different from all the things I've drawn so far. It's the following way. This is just an example. I have the zero line of the energy. This is V of x. This is x. And then I put an attractive potential here. So, and here is minus V0. And then I put a barrier here with a V1. So what I'm going to aim at is, you see, if V1 would be extremely large, there would be, well, if V0 is extremely large, let's begin, there will be bound states here. But these are not scattering states. On the other hand, if V1 would also be infinite, you would have bound states here, but they could not escape. So suddenly, if I combine these two, I put a V0 and maybe a larger V1, I can almost create bound states here, but they're not really bound states because they can leak out and produce scattering states. But these are going to be resonances. This part and this being attractive, trying to keep the particle in, and this being a barrier, can combine to produce a state that gets trapped here and stays a very long time. We'll have a very long time delay. And that's a phenomenon of resonances. We need to trap the particle somehow. And we're going to see now the details of how this works and what the properties are. Now, it's going to be very interesting that actually these resonances occur at some particular energies. And they have different properties, but we can identify energies of resonances. And these are not bound states, They're just resonance. They eventually escape. And they're not normalizable, really. But in some ways, they behave as bound states for a while. They stay there for a while and do nice things. So let's set this up. Now, we're going to spare you a little bit of these calculations because the important thing is that you know how to set it up, and if you get an answer, you know how to plot it, how to get the units out, how to try to understand it. So that's what we're going to do. I'm going to put an energy here, an energy E, and I'm going to restrict E to be less than V1 and greater than 0. I don't expect true resonances beyond, because the particle just bounces out and doesn't get trapped. The phenomenon of resonance is a little more intricate than just having a long time delay. There's more that has to happen. Another thing that will happen is if the particle spends a lot of time here, you would find in the spirit of resonance that the amplitude of the wave function here is going to be very big. So you will scan the energy and the amplitude will be normal, 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 and suddenly for some energy, boom, it becomes very big. And we're going to do that. The way I'm going to develop that, we're going to calculate this, plot these things, and we're going to ask whether there's a mathematical condition that picks resonances. Well, how do I, if I want to explain to somebody in 30 seconds, where are the resonances? How do you calculate them? You cannot tell that somebody, okay, calculate it for all energies, do all the plots and see some peak in something, and this is a resonance. This is what we're going to do to begin with, but then we'll get more sophisticated. So let's put K. So let's call this K prime, the wave number in this area. Kappa here, because it's a forbidden region, and K over here, as usual. So K squared is 2me over h bar squared. K prime squared is equal to 2m. The total kinetic energy is E plus V naught over h squared. And kappa squared is again similar formula, but this time is the energy differential between V1 and E. So 2m V1 minus E over h squared. All of these three numbers are positive, and they are the relevant constants to write wave functions. So we have to write a wave function, and I'm going to write the wave function because it takes a little tinkering to do it in an efficient way. There's one that you don't have to think, you just have to remember. It's the one outside. It's the universal formula, e to the I delta sine kx plus delta is valid for x greater than r. This one we derived at the beginning of our analysis of scattering. How about the other region? Oops, I should have put letters here. These are A and 2A for the positions. And therefore it's not R in here. Well, it's R is the range of the potential, but here is 2A. How about the other one? In this region, it's kind of simple again. The wave function has to vanish here, has to be sines or cosines of k prime. So it has to be a sine function of k prime. And we Since we don't put an extra constant in here, we cannot put an extra constant here, there must be a constant here, a sine of k prime x. And that must be for x between 0 and a. We use the k prime, the wave number there, and there is a. And what we were saying about resonances is that, well, a may depend on k. And when you have a resonance, A is going to become big. Presumably because the particle spends a long time inside the well. And now I have to write this one in here. And this is the one that you can do a little bit more work, or do it kind of efficiently. In that region, we have exponentials, so I could have e to the kappa x and e to the minus kappa x. Or I may want to have sinh of kappa x and cos of kappa x to write my solutions. But I actually don't want either of them too much, because I would like to write an ansatz that almost imposes continuity in a nice way. So I could use sinh of kappa x minus a and cos of kappa x minus a. These are all solutions. You can choose whichever pair you want. So for example, if I want to implement continuity with this thing, this wave function, I want to write something that I don't have to write another equation for continuity. So I'll write a sine of k prime a. So far, this wave function at x equal a coincides with this one. But this is no wave function yet, no the x dependent, so I have to put more. But then I know that cos is 1 for x equals 0, so I put here a cos kappa x minus a. And now this is a solution that matches that one at x equals a. At x equals a, the cos becomes 1 and matches. But this cannot be the complete solution. It's not general enough, so you have to put a b sinh of kappa x minus a. And this won't ruin the matching, because at x equal a, that second term vanishes. So we're still matching well there. And, well, the matching here is non-trivial, will impose some conditions. So you still have to match derivatives and do a little bit of work, but not too much work.